Hello, fellow children. Okay, that was kind of a strange, obscure reference to the officially old thing that's going on in the in the chat at the moment, in the pre-show chat. I'm here, I think. Am I here? I'm here. You are here, and that is all that matters. We are here. So, good morning. A heap of people. Good morning, Don S, Gerald42, Mitch, Scott Miller, Russell Rennie, Stephen George, David C, Immy is here, Gavin Jackson, Tabraze, Crispian is here, and John Whips, Amanda. I am just going to click through some names on the list now, mark them off. This is like roll call at the start of school, isn't it? It's like, are you here? Are you? Please raise your hand if you are here. Okay, I'll get myself back into the chat. Oh, Cassio is also here. Citizens demand an acknowledgement of country. Yes, yes, absolutely. Thank you for reminding me, Mitch. I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. And on that subject, hang on. I'm just going to look something up. For those people who are in Melbourne, this is, I'm gonna bring something up on screen in a second. Where's the button? That one. This one. Belgrave Survival Day. If you happen to be in Melbourne and want to come along next Sunday afternoon, what time does it start? I'll be streaming when it starts, but there is an event happening next Sunday afternoon, and it is going to, yeah, there'll be lots of stuff happening. So come along. Where am I? Chat. Yes. Okay. I'm going to leave that on the screen for a little bit while I am chatting to people. Oh, a whole lot more people have come along, I think. Simon is here. Paul Schultz. Any mules? So today what I'm going to be doing is continuing a little bit of the Testomatic. Yes. Testomatic. So this, the big reveal. There's, yeah, I didn't really explain what this is. It is kind of like a festival would be the closest way to describe it, I suppose. And there are going to be food trucks and performances and different things. So basically, in a park area. So come along to hang out on what should be hopefully a very pleasant afternoon. Looks like it's going to be mid-20s or something, and grab some snacks and see some interesting things in celebration of the native peoples of Australia. So this, okay, where we left things, I'm gonna Gavin asked, have I time to make a warm cup of tea? Okay, you may have time to make a warm cup, but not a hot cup. You definitely do not have time for a hot cup. That time has passed because we are getting straight into it. Rod is here as well. Good morning, Rod. Did we decide on a connector? Asked John Whips. Oh, we did. And this week has been a very eventful one in terms of Testomatic development. And I have gone beyond deciding on a connector. I have rethought the whole power issue. So I'm going to give you a very I'll try to give a very brief what is it? I'm trying to remember the quote from Princess Bride. Something like, okay, I will tell you. No, there is not time. I will summarize. Ah, TTS is working. Yes, I just had to turn the volume up a little bit. Oh, someone, what is the quote from The Princess Bride about I will summarize? I think it was Inigo Montoya who said it. Princess Bride, I will summarize. I will summarize. No, I did a search for that and it's just giving me summaries of The Princess Bride. Someone will remember that quote, I am sure. It's a few years since I've seen that movie. Ah, there, that's it. Thanks, Paul. There is no time. I will sum up. But what was the line before that? Oh. Okay, here comes Henrik's quote. And Henrik says,
Testomatic.
Hello, Testomatic. What is this? It is now 6 minutes into the stream and I am on topic. We cannot be stopped. We're going to make progress. Well, there is no time. I will sum up the progress from during the week. Last week, where we left it was me debating how to handle multi-volt I/O and being able to support digital I/O, analog input, and analog output. And by analog output, I mean true analog output using a DAC, not just PWM, which is like a square wave approximation of analog output. And it's analog in the sense that it's kind of an equivalent amount of energy if you graph the area. Like if you plot the area under the graph of the square wave. So
Not
you
enough
can,
squirrels this week.
there will be squirrels. Okay, Stephen says we need a solid few minutes on topic before we can declare it's on topic. I will do my best. 1-bit analog, yeah, Donis says. PWM is 1-bit analog. That is not so good. So what I need is digital I/O, analog input, analog output at 3.3 volts or 5 volts. And that is the issue. So what I ended up doing was, at the suggestion of someone in the chat, I can't remember who, sadly, I decided to switch to a different, yeah, I've got other tabs here open that I will show you in a second, that I will do the big reveal. So I switched to a different I/O expander, an I2C I/O expander, and it supports all pin modes. So it's got, you can do digital I/O, it can do, in fact, I'll just show you the, where are we? Not there, not there. Ah, got to come back to here. I/O mod. Okay, I/O mod. It's incredibly simple. So this is a chip that, yeah, here we go. The AD5593R. So it's got I2C, and I believe there is also an SPI version. I didn't pay that much attention. So it's got I2C, there's a reset pin, and then there are 2 power pins. The V-logic pin sets the voltage at which these I/O pins operate, like the I2C interface. So what we can do is have 3.3 volts applied to V-logic, and then our interface will operate at 3.3 volts. But internally, it is semi-isolated, not really truly isolated. And there is this second power pin, VDD, which I'm calling VIO because it makes more sense to me. On the datasheet, they call it VDD. I prefer to refer to it as VIO. So it's voltage I/O. It's the, or it's like an I/O, a VREF, really, in some ways. It's not an ADC VREF, but it's like the VREF pin on the Arduino extended headers where they added a VREF so that you could detect what the I/O voltage is of the board. So the voltage that you apply to the VIO pin, the VIO net, is the voltage at which the I/O pins operate. Now, what makes this such a beautiful thing is that we can have 3.3 volts here talking to the Raspberry Pi, and then we can have 5 volts on the external side. So this acts as a built-in level translator. So what we can do is have 5 volt IO on the external side, or on the test pin side, 3.3 volts IO on the internal side, or you can do 3.3 on both, or you could do 2.7 on the internal side and 5 on the external, or 3.3 on the external, or whatever. It'll do anything from, I believe, 2.7 to 5.5 volts on either of the IO, on either of the power rails. So this chip is the core of the solution. Just the existence of this chip gets us a very long way to the end point. But it raises an issue, and this is where the debate was last week. Because what I had with the design as it stood last week was the 5593 chip directly on the Testomatic as part of the I/O. So it was all exposed in here. And I'm going to open a couple more things in preparation. Come back to here. Where are we? Back to here. PCB assembly. That'll do. I'll open that one. Going to open some 3D models as well, just because it's a nice way of looking at it. It gives you, in many situations, it gives you a better concept of what's going on. So what I had was the AD5593s integrated directly onto the PCB. Well, I didn't actually have it fully integrated yet. I had it in the schematic with the plan to integrate it into the PCB. And then there was the question of how do we decide the voltage. My vague concept was, what I would do is provide 2 power rails. There would be a 5 volt power rail and a 3.3 volt power rail. And I would switch them onto that the voltage reference pin under the control of the Raspberry Pi. So the Pi could decide, based on what it's going to test, whether it wants to run its I/O at 3.3 volts or 5 volts. Okay, so that means we need some kind of a power switch. In fact, we need 2 power switches per I/O chip if we're going to be able to control them independently and have some I/O at different voltages. And that was the crux of my problem, being able to figure out how to do that. And right now I'm regretting turning off the air conditioner because the temperature is rapidly rising in here. Oh, it's getting warm. Maybe, no, I won't. I was just debating opening some doors, but I won't. That would probably make it even worse. So the problem was, how do we switch the voltage rails using some kind of high side drivers, or yeah, Stephen says turn the aircon back on. That puts a noise in the background. Okay, so if we have, I'm going to draw a diagram, I think, because I'm doing the hand wavy explanation thing, which does not work that well. So let's switch over to here. Important warning. What? I'm getting I just got a notification on my wrist for something that I don't understand. Oh well. Nothing important enough to stop the live stream. Nothing can stop the show. Alright, so imagine we've got our AD5593 I/O chip here with all its I/O pins going out.
Said, in here inside room temp 20C, outside temp is minus 6C.
Oh, well, 20C in the room. That is nice. That is a very nice temperature. Minus, what was it? Minus 6 outside, Henrik. Okay, that's pretty cool outside. That is on the cool side. So then we've got our Pi. Then we've got up here, say, a 5 volt rail, and we've got a 3V3 rail. And we might have 2 high side switches going to VDD, and then we've got something like this, and then we want the Pi to be able to control these two high side switches. So this was my vague, and that is on 3.3 volts. So this was kind of very vaguely my concept for what I was wanting to achieve. And that way what I could do is I could have 3.3 volts or 5 volts on these I/O pins controlled by the Pi. Then when the Pi loads a test profile and it knows what device it is trying to test, what it would do is turn on the appropriate high side switch and supply the reference voltage to this. And where we were getting to last week was thinking about putting all of this on a sub-module. And we were looking at maybe making like a large daughter board that would plug in with a whole bunch of connections. And those connections, so what we would need is somewhere around 60 ballpark pins. I think 60 was the bare minimum, and a couple more could have been useful, because we would have 56 I/O pins. Then we need ground, we need power, actually we need several powers, we need SCL, SDA, 54. I can't think. Yeah, so 54 I/O pins. So we need 2 powers, a ground, SCL, SDA, like and reset, and I think that takes us to 60. So yeah, I count good, just like I speak good. And that then would allow us to put 7 of these chips onto a breakout board, and then it could be replaceable, it could be upgradable. It gives us all the flexibility. And if we're doing a test and it destroys the I/O, like say you have a device under test that inadvertently exposes 24 volts onto an I/O pin or something, and boom, it blows your tester's I/O pin, you can replace that module and then you can keep on working. This was the problem that I was trying to solve early in the week, was how to achieve this. And I was buzzing, it was buzzing around in my head, couldn't get an answer. I was wandering around the factory, wandered in next door, was talking to Lachlan and Jamie, and ended up nerd sniping them into a whiteboard session where they were trying to help me solve this problem. So we went through a big discussion where I was trying to explain this problem of all the combinations of I/O pin modes that I wanted, etc. And that discussion made me very much rethink the power strategy and distill, you know, when you've got a problem. Say, this is generally my experience. It's not always the case, but generally, this is like the sweet path of how you want it to work out. You have a problem in your mind where you have various conflicting requirements. You have a goal that you want to achieve. You want something that you want this circuit to do, or the system to do in general, not necessarily, it's not just an electronics thing, this is just like a life thing. You have a goal that you want to achieve. And in your head, there are these conflicts where if you do it this way, then you're making this compromise. And if you do it that way, then you're making these compromises. And you're trying to find the least bad path through. And often in doing that, the system becomes more complicated the more you try to allow for exceptions. And building logic and rules, different parameters into the system, and it doesn't feel right. It feels like you are overcomplicating it, and for me the experience is just like a discomfort in my brain, and I'm thinking, no, this is not it. I need to be able to reconceptualize the problem or distill it down to something. And when the golden path happens is when a simple solution emerges that achieves all of your goals potentially giving you even benefits that you hadn't even thought of before, and it is simpler. So ultimately, simple is beautiful and often functional. You can't always do it. Sometimes you need to build a complex system. Sometimes you have to have all of these rules and build layers into things to make them more complicated. But what ended up happening was, after that whiteboarding session where I'd been laying out the general problem and Lachlan and Jamie had thrown some ideas at me, and it was all sort of gestating in my brain, and the solution that we came to sort of collaboratively, because it definitely, I would not have arrived at this result without that conversation, was, why do we even need high side drivers? Let's scrap that. Because conceptually what we're doing here is controlling the reference voltage of these I/O chips. And I was fixated on this path of, how do I control this reference voltage from the Pi? How about we go radical? Get rid of this, and you don't need the Pi control. Instead, this is the genius bit. What you do is, we have our test module over here. Is that on screen? Yes, it is. So we have our test module. We are passing all of our I/O pins through to here. What we do instead is we take our voltage, our reference pin, and also pass that to the module, VIO. And then these are the I/O pins all down here. The reference module, the test module.
Said, I have arrived.
Aha! DIY is here! Nice. And all we do is, on the test module, bind that pin to either 5 volts or 3.3 volts, depending on what you want that block of I/O pins to run at. And then you have I/O pins at the voltage requested by the test module. So simple! It's one of those things where the solution is so simple and so elegant that it just, you know, that feeling of, oh, that's it, the problem is solved. That's what this is like. So we've got, because the test module already has the power rails on it for whatever it's going to need, it could even have its own onboard voltage regulator. It doesn't matter. Like, you could be running 2.7 volt logic or something on this. It doesn't matter. As long as that voltage is available.
Pro 24 mount HS now.
Aha! Who's been a supporter? Amanda has been a supporter for 24 months. Nice. Scott is about to say...
Scott Miller said, so the I/O chip is actually powered from the DUT.
Almost. Yeah, very, very close. It is powered from the test module, which has power links to the DUT. Yes, the logic side of the chip is powered still, so this will be powered from 3.3 volts. I've got a sneeze coming on, I can tell. So 3.3 volts for the logic side, because we've still got I2C communicating between the Pi and the I/O module. But the reference voltage that tells the I/O module what voltage to run its I/O at comes from the test module.
That's what I meant.
Yes. Yep. Cool. So, yes, Scott is absolutely correct. You can consider this to be the device under test. It is the, well, kind of. There is the device under test, and then there is the test module, which it fits into. So, test module, and then the device under test is what goes into this. So the voltage is being supplied back on pins on this header, and that is coming back in here to this I/O thingamajigamy. And that means that we might have, all right, the canonical example for this is what I've been working for. In fact, I'll unplug it. This one, I assembled this after the stream last week. This is the test breakout for the joystick interface module for the water cannon project.
Scott Miller said, "Dut mod."
Dut mod. So this is, so this device has a joystick. You can see there is raw X, raw Y, right trigger, left. These are inputs coming from the joystick. The joystick is a 5-volt device. It provides 2.5 volts when the joystick is in that center position. Deflect it and it goes above or below 2.5 volts. So we need a 0 to 5 volt ADC to read, we need a 0 to 5 volt DAC to generate the signal to simulate the joystick going into the board. But the board runs at 3.3 volts. So what we would want to do in that case is configure one of these modules, one of these I/O chips, to run at 5 volts by tying 5 volts back down this reference line, and that allows it to generate 0 to 5 volt analog signals, which can be used to pass through to here to simulate the Hall effect joystick. But we want other modules to run at 3.3 volts so they can interact with the I/O of the board that is actually running at 3.3 volts. So, okay, that brings us to actually implementing it, which I did on Friday night. What I did was to the Bat computer. What I did was this. No, not that. What am I doing? Oh, it's got too many tabs. Can't see them all. IO mod that. Yeah, okay. So this circuit, this schematic that I was showing you earlier, this is the IO chip. And what I did was basically turn it into a DIP format module. So you might be familiar with the, where are we? Step, stick, this thing, which is commonly used on rep-wrap style 3D printers and different things. Where are we? I need a picture of one. That's what I was looking for. Okay, so these are little modules with a defined footprint, and you can put different drivers on them. So the idea is that, let's go back to step stick images. This will work better. Yeah, so with this, it is a footprint for in this case it's an A4988 stepper motor driver, and it's got standardized pins. And then you can get different versions, like this one. What is this one? This one's a DRV8825. So it's a different stepper motor driver. This one, this one's the A49, etc. What's this one? Different one. But anyway, the point is, this pinout is standardized, where you've got enable, you've got a reset, step and direction pins, you've got VDD and ground. There are the outputs here going to the stepper motor. There is the motor power supply voltage on here. This is a defined pinout, and you can make different modules that are plug-in compatible. They will have the same step and direction pins, the same motor pins, the same power pins, but you can create modules with different capabilities. So the A4988 is the old style Allegro type stepper motor driver, but then you can do ones with the DRV motor driver we just saw a second ago. This one, the DRV8825, and that means you have the ability to make modules that plug into that same footprint but might have better micro stepping or higher current capability, or you might want to make a really cheap one, so you're building it down to a price. But those modules become interchangeable, and that is what I have been working on with this. So hang on, I'm just going to find a folder, because I've just put all of this stuff up on GitHub as well. In fact, rather than do that, I'm going to open it on GitHub. GitHub. Here. Where are the repos? Give me a repo. A repo under the gum tree. Yeah, so this is now on GitHub. And this is the digital print, put it back. What? Esbro is trying to write code into the chat. Luckily, there is no parser that is dealing with code in the chat at the moment. IO module repo. Okay, so this is a very similar concept to the step stick, but instead of being a stepper motor driver module, it is an I/O module, and it's got the 8 I/O pins down the right. In fact, if I come down here, you'll see the pinout, and I put dimensions and things in here, so there's a mechanical drawing. So it supports 8 I/O pins down the right hand side. There is ground here. There is the I/O voltage, which is the voltage reference. There's a logic voltage pin, a reset pin, and then we've got I²C. And that's it. There are 2 spare pins here. I haven't assigned those to anything, but making this a 16-pin dip, and there is a little catch to that, which I'll get to in a second. There is a, yeah, I will get to it. So I thought making it a 16-pin dip and leaving a couple of spare pins here unassigned gives some future capability. For example, it might be desirable in future to make I/O modules that have SPI, and having a couple of extra pins means that we can use like the SEL pin as the clock pin. Then we need, and the SDA pin could be MOSI, and then we could put down MISO and chip select, for example. So these 4 pins, the ones that are currently used for I²C and the 2 spare pins, could form an SPI interface, because maybe you want to put something like a high-speed DAC on here, and it doesn't even necessarily need to support 8 channels. You might make a module that has a high-res, high-speed ADC with an SPI interface, and it just reads off 1 channel or some small subset. Yeah, so this, for my own particular purposes, this module will do the job for what I need. These are the features. But it does allow future expandability. Now, the caveat that I was referencing earlier is that this is all metric. This is not a 0.1 inch pitch thing. And the big downside to that is that it's not going to plug into a breadboard. But I weighed it all, and I thought that was a compromise that I was willing to make. And you could make an adapter for a breadboard if you really wanted to. That would be trivial to do. But for the purposes of building this onto a carrier PCB, it works a lot better on 2mm pitch in terms of size and spacing and that sort of thing. So if we go to, oh, and I updated the Testomatic. Testomatic? Is that where it is? Yes, I updated the Testomatic repo yesterday as well with the new design, and this is a screenshot of the updated design.
3D print a metric breadboard.
Ah, yeah, metric breadboards. Yes. So the Paul Schultz said, "Oh, built-in oscilloscope." Yes, exactly. You could basically build a scope into the Testomatic by putting a module on here. So what you can see in this shot is that I ended up modularizing each of the I/O blocks independently. So last week we were talking about having a daughter board that plugs in with a 60 plus pin connector that would do all of the I/O. However, there are some downsides to that. One is the connector itself was going to be a bit of a pain. Two is it doesn't allow you to mix and match I/O. If you have a special case where you might want a few of these standard I/O modules, and then the Espero said, why'd they design breadboards in a way you can only use one side's GPIO? One side. But isn't that just a function of the width of the module? I don't know. Anyway. Yeah, so what you could do is mix and match. If you have a specific testing requirement, you could put, say, a high-speed, high-resolution ADC into one of these modules, into one of these footprints, and configure that in your test setup. Or you could just use these default ones. I left a couple unpopulated in the photo just to show that they are pluggable modules. And because of the way the pins are assigned, they're numbered right to left, so that's module A, B, C. So in the actual design, Scott Miller says, might relate to the fact breadboards were designed before MCU modules were a thing. Yeah, true dat. TM mod. I know we'll get back to that in a second. I'm going to ignore TM mod for now. We'll go back to Testomatic. And here. Alright, so in Testomatic, what I did was, this is the new way it handles its I/O. It has a series of these ports. So port A, port B, etc. So there's I/O port A, pin 0 through 7. And this is the footprint that the I/O module plugs into. And you can see that we've got 3.3 volts coming in on the, what was that pin? It is the, oh, it's the digital logic pin. What's it called? I can't remember. What did I call it? Anyway, so we've got VIO, which is what sets the I/O voltage. Oh, VLogic, that's what I called this one. So 3.3 volts is going to VLogic. Then we've got a reset pin, so we can reset all the I/O modules. And we've got I2C, plus a couple of spare pins and ground. And so what I did was I grouped it and called them by a number, because in the original design, in Testomatic, the I/O pins were just numbered 0 onwards, so 5, 6, 7, 8, 9, etc. But instead what I've done here is grouped it into port A, port B, port C by module, and then the pins are named by port number and pin number, like bit within that byte. So each I/O block is a byte, and then we have bits within the byte. And part of the reason I did that, I split that numbering up. Two reasons. One is that this is much closer to the way I/O is traditionally referenced in microcontrollers. So people are usually more familiar. Well, in Arduino land, not so much, because pins are just numbered. Like if you've got an Arduino Mega and it's got 50 something I/O pins on it, they're just numbered 0, 1, 2, 3, 4, etc. all the way through to 52 or 54, whatever the number is, I can't remember. But on the microcontrollers themselves, they're typically broken up into ports, because internally, the way these are mapped in memory, each port is 8 bits, and then each pin is 1 bit of that byte. But the other, and I think this is actually more important consideration, is that conceptually, when you are designing a test system, you need to make a design decision about the reference voltage that you are going to use for your I/O. And that is going to be assigned on a per module basis, which means that a port is going to have a voltage set, and it needs to be very clear. So if you are thinking about I/O pins and you're thinking, I/O pin 27, I'm going to assign that to like one particular purpose on your test breakout. Now I/O pin 27, I can't remember, is that one running at 3.3 volts or is it running at 5 volts? So what I wanted to do was make it really obvious, so you can think of it in terms of blocks of ports. you might assign ports A, B, and C to all be running at 3.3 volts, and port D to be running at 5 volts. And now you know any of the pins that are in port D, so like D4, D3, D6, they are all 5 volt I/O pins because they are in port D, and you have assigned the VIO to 5 volts on port D. So by changing the pin numbering into these blocks so that we've got one
Scott Miller
byte.
said, Arduino is awesome. Got new BS into electronics. Arduino is evil. Taught new BS bad habits.
Yeah, everything has its good and its downside. Its upsides and its downsides, its goods and its bads. I very much fall into the Arduino is awesome camp because I think its upsides massively outweigh its downsides. But yes, you're right. By simplifying things and abstracting and hiding what's really going on in some situations, it both provides a low barrier to entry, and it gives people the wrong idea of what's actually happening sometimes. But abstraction can also be very good. Anyway, I won't chase that squirrel. Abstraction layers are what allow things like board profiles to allow the same code to be recompiled against different targets without changing the code itself. And that is a good thing. So, yeah, I hope you can understand what I'm saying here about breaking the pins. So I/O pin 0 through 54 are broken up into these 7 blocks of 8 pins each. And then you can assign the I/O reference voltage, the VIO, for each one of these independently. And that VIO voltage, so IOA for example, this is going to come back to, if we come back to here, so the unfortunate thing is I've had to change the pinout on this big connector, which sucks because it means that my test modules, the ones that I've already made, are no longer going to be backward compatible. No, they won't be forward compatible, I mean, with the new version of Testomatic. Luckily, I've only done a couple of test breakouts, and they will be very, very easy to update. In a moment, you will see how easy it is to update them to work with the new pinout. Now, on the old pinout, if we zoom way in here, this pin here, for example, pin B52, was a ground. And there were a pair of grounds in between each block of 8 I/O pins. So all I did was take one of the grounds...
Bodge.
Yes, bodge. So take one of the grounds for each of these I/O blocks, and I changed it to the voltage reference pin, like the VIO pin, for that block. So IOF VIO is the reference voltage pin, the I/O reference voltage, for block F, or module F, likewise for module G. So now what we can do is on the test module, all you do is link that pin, say we want module G to be running at 3.3 volts, we just connect pin B57 to 3.3 volts, and magically it works. Okay, now, a couple more thoughts on the subject. One of the questions or the discussion points that came up during that whiteboard session during the week was, where is configuration encapsulated? And my concept of the configuration of these I/O pins was that it would be set in a config file defining the test suite for the this particular target, and it would be loaded by the Python test runner, which would then configure the I/O voltages based on the config. And what that means is that the Raspberry Pi would be using its I/O pins to set all of these reference voltages. And it would be under software control. So that puts the encapsulation of that config data into the config file. However, what we have now is the configuration has been pushed off to the test module. So the configuration of that voltage is set in the copper on the test module. So if you plug in a different test module, you get different I/O voltages, and there is zero software involvement. There are no I/O pins required. It's just magic. It just works. And that is the holy grail. We plug in a new test module, all of the I/O reconfigures itself. There is no danger that the software will screw up and not set the voltages correctly. It's not possible for that mistake to happen because that reference voltage now comes from the test module, which is very cool. Espero Kelly says, analog config. Yeah, kind of. Don S said, do you have opto isolation or something similar to protect your main board? No, I do not. So at the moment what we have is, on the main board we've got the Raspberry Pi header, and the Raspberry Pi is connected to a number of things. It's connected to EEPROMs, it exposes SPI, and it exposes I2C, wherever that is, up there, and a number of I/O pins. There is tester reset, but there is not really a huge amount of, the external button, and also serial for the infrared camera. But there is not really a huge amount of exposure of the Raspberry Pi itself. The Pi is mostly isolated from the device under test. All of the interaction with the device under test happens through these I/O modules. So if there was any isolation that was required, it would be done on the I/O modules. But now that each of these I/O ports is on a separate module, it means that worst case scenario, if you fry one of these modules, you can unplug it and replace it. And it's not a huge deal to do that. Now, one thing I need to think through is how to handle physically replacing the modules, because at the moment they're obscured by the chassis. So, yeah, I need a solution to that. So that comes down to the mechanical design as well. Okie dokie. And here we've got a multiplexer. A multiplexer, you say? Why do we have a multiplexer? That is because the AD5593 only supports 2, count them, 1, 2 I2C address. And that sucks because we need 7 of them. So there is an address pin, IO mod, if we come along here, there is one single solitary address pin on here, which means we cannot set 7 different I2C addresses on the test modules. We have to handle it another way. So in the, where are we? Here. So in here, what I've got is an I2C multiplexer, the TCA9548. We've got the I2C coming from the Raspberry Pi, and then it gives us 8 I2C buses on the external side, and we're using 7 of them. They all have their own pull-up resistors. They're all running at 3.3 volts, and then they go to each of the I/O blocks here. So one of the questions that some people might be asking, and it might have already been set in the so it might have already been asked in the chat, which I have not been paying enough attention to, is speed. Yeah, speed is an issue. We're dealing with a whole bunch of I/O pins on I2C I/O expanders, and even worse than that, we are multiplexing the expanders, which means that if you want to read from a specific pin or write to a specific pin, you need to first use the I2C multiplexer to make sure that you have selected and are addressing the correct I/O expander, and then you need to communicate with that I/O expander over I2C and read or write its pins, or do whatever you need to do. So this is not a situation where we have super high speed I/O. You're not going to be bit banging I/O.
Scott Miller said, John regularly loses the chat.
Yeah, I do, along with my mind. Yeah, so we're not going to be doing high speed bit banged I/O or anything on this. This is more for a case of we want to set some I/O pins, we want to read some I/O pins, let the device under test do its thing, read that, read the state of the pins, check them against whether it matches our assertion about what the state of the pin should be, etc. So this is for low speed testing. But it does allow for the possibility of high speed in future, because we can potentially do SPI on those modules, and you can also do SPI with other modules or with other devices directly on the test breakout. So you don't have to go through. Yeah, the idea is that these I/O pins, the ones that we are providing on the header being passed through to the breakout, are like I don't know how to put it. They are
Mitchell R. said, you passed through a USB in the main DUT board, right? Then yay should not be an issue if speed is needed. You can do DUT specific stuff.
Exactly. So my goal here is that if you look at the header that goes through to the device under test, or to the test breakout, we have all of these I/O pins, but these are general purpose, running through I2C. They're only 12-bit ADC and 12-bit DAC. They can do digital I/O, so it's like the lowest common denominator. This gives you a bunch of I/O pins. So you've got 54 I/O pins here that you can use for any of those purposes. 3.3 volts, 5 volts, digital, analog in, analog out. That should deal with that's okay, good enough for 80% of situations type I/O. It'll deal with most things. But up here, what we have is we also have SPI exposed from the Raspberry Pi, along with a couple of spare I/O pins. So we've got chip enable 0 and 1, we've got a couple of spare I/O pins, and we've got an I/O pin that can be used as a reset line. So if you wanted to be able to reset part of your tester, you can do that as well. We also have 4 USB ports that are exposed up to the tester, and we've got the I2C as well is exposed up to the tester. So if you wanted to, you could ignore all of these I/O pins and build all of your smarts into the breakout itself, and do it using SPI or USB or whatever you want. It's all there. But the goal is, for the majority of cases, you should be able to just use these regular old low-speed I/O pins, and it'll probably do. Then for the exceptions, that's when you reach for the high-speed solutions like SPI on some dedicated I/O chip that is built into the test breakout itself. But that is not ruled out. It's not, you're not forced to use one or the other. You can use whatever suits your needs, and this is just for convenience. Hang on. Cough time. And my voice is back, my lovely dulcet tones. Yeah, right. So that is kind of where it's got to. And if I switch to, can I switch to a 3D view? Oh yeah, so in order to achieve that, what I did was I switched to a 6-layer board. So Testomatic is now a 6-layer PCB. And if we go into single layer mode, so we've got the top, and layer 2 does that, layer 15 does that, layer 16, which is the bottom layer there, back to 2. So if we have a look at layer 3, it's this one here, and layer 14 is this one here. So the I/O is
Waiting for the DUT that needs all of the I/O plus USB plus SDI plus I2C.
Yep. So an error has occurred. Thank you, Java. No, go away. No, remind me later. Yeah. Now this is a situation where I may have been able to route this as long to do it. Doing it as a 6-layer PCB means that I could group quite neatly, and I get a bunch of extra ground planes as well. So what I have now with the 6 layers is from top to bottom, now, is my memory correct? I think this is what it is. Ground, and I've got polygons everywhere. So if I do if we do a polygon pour here, so there is a polygon pour on every layer. So top layer, bottom layer have these polygon pours. So top to bottom, it's ground, 3.3 volts, ground, ground. No. Yeah. Ground. I got to get my fingers right. Okay, it is ground, 3.3 volts, ground, ground, 5 volts, ground is the layer stack up on these polygons. So if we have a look on layer 15, which is actually the second bottom layer, and have a look at the polygon there, that's a 5 volt signal. So yeah, so that's a 5 volt plane, and layer 2 is a 3.3 volt plane. Layer 1 is ground, layer 16 is ground, and layers 3 and 14 are also ground. Yeah. So the result is a reasonable level of isolation between all of these signals. If we look at, yeah, we've got pairs of signals here on layer 2, we've got pairs of signals on layer 3, pairs on layer 14, and pairs on 15. And they are all bounded. So those are all internal layers. There are no signal traces that are exposed on external layers of the board. Now, a couple of them are on power planes, but that's some signals may die, but that is a price I am prepared to pay. Yeah. So the result is that each of the layers actually looks relatively simple. Like if you look at layer 15, layer 14, they look really simple. Layer 3, there aren't that many traces on them, but because of the way the routing works from these pins or from these modules, going to this big connector which has got 4 rows of pins on it, and you've got to thread the needle between those pads.
Scott Miller said, "Gonna make bodging a bitch."
Yeah, but there won't need to be any bodges. Scott, this is going to be perfect. Perfect. First time. First time. Every time it's going to be perfect. So, yes. I think I could have routed this board on 4 layers, but it got to the point where I was looking at how these signals were going to route between each group of 8 pins here and each group of 8 pins here, and it would have turned into a total rat's nest as I was trying to do routing through here, threading the needle
Scott
between
Miller
all these
said,
pins.
"Such an innocent lad."
Yes. Yeah, it is only version 2.2, so we should be converging on something sensible by now. Yeah, Gerald says, we don't need no stinking bodges. Yeah. Or I just rev the board, which is my current solution. Yeah, so anyway, it ended up only taking me,
So
I don't
you're
know.
sure it's 100 without ENY errors?
Yes, Henrik, I am sure it is 100% without any errors. So switching to 6 layers made this routing really easy. It was a very simple job, and it only ended up taking me, I don't know, 4 or 5 hours, something like that, to reroute this entire part of the board, including moving a whole lot of things. So I moved the USB hub, I moved parts of this power management, the infrared camera, and the external button. These were all previously up here somewhere. We've got the multiplexer added in here. So there's the I2C multiplexer and the 7 I/O modules. Yeah, and then we've got the USB ports coming down here to the hub, and the USB connector here that goes to the Pi, and the header there that goes to the Pi. So I think that this is now ready to, just because it's cute, I think that this is now ready to send off for fabrication, and I think that the I/O module is now also ready to send off for fabrication. Simon said, assembly of the new PCB next week? No, I am pretty sure that I won't have it back by next week. If I send these boards off for fab this afternoon, the penalty time on the 6-layer PCB means that I will not have it back physically in my hands by this coming Friday, which is when it would need to be delivered to be ready to assemble next week. So, test mod. I'll get to that in a second. I/O mod. Yeah, so this is my concept for a general purpose I/O module. Oh, and also you can see that I exposed that address pin for the 85593. What I did was I put a pull down resistor on it. I think it's this one here, R1. So that's a pull down resistor to set it to the default address. And even though we don't care about it, just because I could, I put a solder jumper on here so that if you bridge across that, that pulls it up to the VIO, not VIO, it pulls it up to the V logic voltage, and it sets it to the other, yeah, the render here is a bit screwed up because it's showing...
Said, still faster than buying a new Toyota.
Yeah, true. The render here shows some stuff that isn't actually part of the silk screen, so that's why it looks all jumbled here. But it's either going to be hex 40
no.
or hex 4E, depending on whether that, depending on whether you bridge that solder thing or not. Because in other applications, you might want to use this module for something else. You might want 2 of them, and you might want to set them to the 2 different I2C addresses and not use a multiplexer. So you can do that. Even though I am not going to do it, I allowed for it. And this is the end result. So this is the updated, fully routed V2.2 bodgeless Testomatic carrier PCB with everything relocated and with the footprints for the I/O modules.
Such pointy corners.
Such corners. And on the I/O modules, you mean? Yeah, I considered rounding them, but if I want to panelize them when I get them fabricated, and I'll just get them V-grooved. And if I round these corners, like if I put a 1mm radius, actually what would I do? Yeah, it'd be a 1mm radius, because this is a 2mm pitch here between the pins. That is 1mm from that the center of that pin to the edge of the board in both directions. That's 1mm. So if I put a 1mm radius on here, that radius ends up on, I end up with like a clover leaf, or whatever, no, it's not quite a clover leaf, it's like a reverse clover leaf. I end up with 4 interlocking semicircles in the corner in the joint between the boards, So, and I don't want to mouse bite it and have them separated. I just want a big grid of these on the panel. So I thought I would just be boring and probably for the first time in a long time design a board with a square corner. Being so lazy. So yeah, you can see I've just named the things on here. So IOD, IOE, and it's actually pins 24 through 31 and then 32 through 39. But the we would reference each of these pins as like E0, E1, E2, E3, etc. Yeah, so that is done.
Scott
What
Miller
else?
said, quality time with sandpaper.
No. Assembly, where did I have a 3D model here somewhere? Oh yeah, somewhere. Here we go, Testomatic assembly. This one. Is it this one? No, I don't think it is this one actually. I think this is an out-of-date assembly. I think the assembly that yeah, this is where the major parts fit together. Oh look, you can see it's got the old I/O board in it. So this is what it used to look like with the pair of MCP 23017s and ADS 1115s and the DAC that I can't remember the part number of. So this is how it was before I ripped up all of this part of the board and rerouted it. So get rid of that, go into chassis and chassis assembly. 10th of the second? No. Must be more recent than that. Is this the recent one? 10th of the second.
Scott Miller said, new version looks massively neater.
And yes, more flexible. Is that the new one? No, that's the old one as well. I don't know where it is. Where is my assembly? Archive, MJ, test modules. It's not that one. 16th of the second. There's one that'll have been modified only a day or two ago. What is MJ? Oh, I know what MJ is. That's not relevant to the discussion right now. Anyway, somewhere in here, I have an assembly that shows it all. Archive. Maybe I moved it into archive. I may have, because I was moving old stuff in. Nope. Nope. Oh look, here's the riser. This was from ages ago, July last year. This was when we were going through that concept of switching from IDC cables, this was a transitional thing, to the PCI connector. When I was thinking of putting this in vertically, and yeah, cool. Memories. All right, I'll get rid of that. And next thing is, what will I leave up? I don't want that. I'm not going to need it anymore. I don't need... Do I need this? I possibly do. All right, the relevant bit now is changing the test breakouts themselves. And this is where I kind of got up to as of last night. So the breakout version of this is, it's like my skeleton or my reference design. And the idea is that this is what other breakouts will be derived from. So it's a bootstrap, or it's a starting point that allows you to very quickly create a test pin breakout for whatever your project happens to be. Now you can see here this is in a state of transition right now, because previously, as you can see from the silk screen, we had the 24 digital I/O pins, 16 analog inputs and 16 analog outputs, and they were grouped together. But now we have 7 I/O blocks, and each I/O block can be any of those purposes. So they are now all first-class citizens, they can all do anything. And so we don't need the artificial distinction anymore between the digital pins ADCs and DACs. It's just 54 I/O pins. Now what I've done is, for each of these I/O blocks, I've brought it up to a 10 pin header. So we've got the 8 pins of the I/O pins. We have the VIO for that block. So in this case it's IOG_VIO. That's the voltage reference pin for this I/O block on pin 1. So GV, and then FV, etc., EV, so that's the block voltage reference. And we've got a ground pin. And they are all grouped onto separate little blocks of things. And then those signals can be routed to whatever you want on your test pin thing, because your actual PCB is more likely to be about that big. It'll extend up here somewhere, and that's where all your test pins will be. So my job now is to, oh, and you can see I haven't actually finished renaming all of these. So that, so this, for example, should be AV, and that should be A0. So I need to, A0, I need to go through and change the labels on those. They're okay. I was doing them right to left. I don't know why. I was doing them right to the left, so they're okay. G, F, E, D, C here.
Need to change Reverend there too.
Need to change which way what? Need to change rev there too. Ah, yes, I did. It's V1.1 of the test breakout. So where am I? Okay, I'm going to, the next part of this is just it's just tedious. It's just routing and labels and those sorts of things, but trying to make them fit, because what you can see here is the I/O here, this block of I/O pins is what used to fit into this space from here to here, from, if you can see my cursor, from there to there. It doesn't fit anymore, and you can see that it runs across this side onto almost in line with this, this mounting hole, and over this side it overlaps with these pins, which means these are all going to have to move left, and that gap there on the left is smaller than the overlap here. So I'm not quite sure how I'm going to make them fit. I think I'm going to have to do it by moving these mechanical mounting holes up away and bringing the I/O pins closer to the edges of the PCB. So they're going to come very close to the edge of the thing. So in fact, if I, what grid am I on now? 1mm, that'll do. So if I want to bring these so that they come closer to the edge of the board, maybe somewhere about there. If we zoom in on the right, you can see that it'll be a couple of millimeters clear of the edge of the PCB, just in this area, just in there. And then the PCB is going to have to get deeper so that this hole is past these connections. Is that locked? I can't remember what that symbol says. Locked? No. Okay. So what I can do is, for now, I'll just move this up here somewhere. Where? About there will do. Is that in line? Yes. And then this one can, oh, come on, zoom, zoom, there. And then this one can come up so that it's in line vertically with the one there and with that one there. And now I need to, what'll I do? I'll hide the silkscreen layers, and let's do a move. So yeah, I'm kind of half getting into doing the actual thing now. There and there. This is probably going to screw up because the radius is a, oh no, that's interesting. That was not what I expected to happen. Okay, let's yeah, I think the corner radiuses are going to screw up. They are, but I can fix that. That's no problem. We'll get that to there, and then we can bring this corner radius up to here, and over on this side the same. And later this will all need to be shrunk down. It's not actually going to be this high. All I'm doing is giving myself workspace within the bounds of the geometry of the board to mess around with putting all of these connectors and things in place. And now you can see that the edge of this connector overlaps with the hole on the vertical axis. Oh, excuse me. And so now if I am brutal, these are length matched pairs on the these are USB pairs here. So these are all length matched, which is why there are weird squiggles and things in them. Or are they? I don't actually remember whether they are length matched or not. No, I don't think they are. They should be. But it doesn't matter. We've had this conversation before. I know people say, you got to length match your USB. And I say, I don't care. Make me. Yeah, I get lazy and fall into the it works for me sort of mindset, because length matching on USB is less important than people think. The actual distance required before you get, at the frequencies that USB 2 in particular runs at, the distance mismatch required before you get a get any problems occurring is bigger than you would think. That is a number that I should have in my head. Like, it's something that would be very useful to know. Oh, that fits better than I thought it would. I can actually move that stuff to the left. Nice. Let's bring all of this across. And I'm not going to put it in the final position yet. It's going to need to move vertically. But I'm just trying to get the gap on the left here. So that's currently about 4.5 millimeters to the edge of that, or 4.3 millimeters. What is it over here? It's about 3.5 millimeters there, so it's slightly offset to the right, but that's okay. The power connection's here. Oop, no, I do not want widgets coming up. And yeah, so now what I need to do is move, I need to clean up a whole bunch of these tracks so that I can then reroute. So let's, excuse me. Let's just get rid of a whole bunch of those. And I should have deleted more.
Scott Miller said, wider gap between the I/O the rest would be a good idea.
I didn't understand that. I'm going to have to read the chat to figure out what you're talking about, Scott. Delete. Go on a little delete spree. Yeah, I need to make some more room for traces coming off there to get across to the power. Yeah, that'll be fine. And more importantly, for the USB traces to get across there. Yeah. Okay, now, where was that chat thing? Scott says, wider gap between the I/O and the rest would be a good idea. Ah, I see. The I/O. So these ones, this one is I/O-A. That's where the I/O pins begin. And then this one is USB. And this one is SPI, I2C, etc. Then we've got power there. Yeah, I suppose what I could do is move these across to the left. If I grab from here to here, and then I move that left by 1 millimeter. So that's where it was. Move it across to there. That means the gap on this left edge now pretty much matches the gap on the right edge, which makes me happy. And there is now a slightly bigger gap. So we've got power here with a little bit of a gap. Then we've got SPI and USB grouped together. then there's a slightly bigger gap, a 1mm gap, and then the I/O here is all grouped together. Yeah, that seems acceptable to me. I do not have any fundamental problems with that approach. I've got to move the fiducial. Stick it. I'll just shove it out of the way somewhere for now. And then, so where are we? I need a drink. I don't know about you. I am going to. I have a cold water here. Here we go. I'm gonna mute myself. Just like sing a song or something. Better. Right. Take Nebula said, don't move the mounting.
Shot of rye.
Ooh, shot of rye. No, just H2O. Wagon Loads asked, does this PCB slide in edge guides? Not edge guides. It is dictated by the position of two things. One is the vertical sides of the chassis, which intersect with two layers of acrylic in the test module. And in fact, I can show you.
Outside the box said, were we meant to all sing the same song?
Yeah, of course you were. You're all meant to sing in perfect harmony. Here. Okay, so this is the back of the Testomatic, the test module, which is here. And you can see there the PCI socket, which we have to align with. And that PCB, where's the angle? There, has to align with the socket. Now the back of the test chassis has two layers which are slightly inset. So it sits on the top layer and it is guided by the layer down. And the result is everything just lines up nicely. So all I have to do is drop the module in. How do I get this angle? Yeah, drop the module in. You can see that it's sitting on the top edge and it can't really move very much. Slides forward. The PCB aligns with that socket.
I do like to teach the wall do sing.
And then you just push it forward. That's it. It's now locked in place. The PCB is engaged with the PCI socket. So that part of it, I am very happy with. It works out really well. You can drop the test module into the top of the chassis, slide it forward, makes a nice satisfying clunk as it engages with the socket, and everything is connected. So that is very good.
How's hunger today? I just finished extra cheese and creamy pasta with sweet chili chicken, and for salad I had.
Oh, Henrik. You're always doing this to me. And pizza. No, I feel like pizza. I was watching a TV show last night while I was doing routing on a PCB. I often have like a show or a YouTube or something just running on a separate, on one of the extra monitors. And the, oh, your mini plugin does not have that housing. Yeah, it could. It could have that housing. It doesn't need to. It will just plug straight in. In fact, I can demonstrate that. Where are some? The Testomatic box. There. I will show you with the current version of that Breakout exactly how it works. In fact, this will give you a, yeah, it's one of those things that does just work, and it is very satisfying. Oh, maybe the PCBs aren't in this box. No, they're not in that box. I had them out because I've been doing a bit of Testomatic stuff over the last few days. Are they in here? I think they might be in the cleanish room. Are they? Or aren't they? Where did those PCBs go? I had those Breakouts somewhere nearby. In the test area. Oh yes, here they are. Here is one. Yeah, I know, you can't see me, but that's a good thing. But you can hear me.
Henrik Ostrov said, what your mini plug-in boards have that you can plug them backwards is their security pin.
Oh, I see. Yeah, the new little modules. Yeah, I don't know. I figure if that gets stuffed up, then it's something that yeah, you can't protect against everything. So were you not talking about this? So this is the existing version of the Breakout. This is the old version of what I had on screen just a second ago. And here you can see it without any chassis around it. It could be mounted in an acrylics like this, or like this, which actually shows you better how it all goes together. But it doesn't have to be. You can just plug it straight into the socket and it just goes in very nicely. And it self-aligns because the edge is here, and it's got the key slot there. There's the key in the middle of the socket. You basically can't plug it into the wrong place. It has to align. Now, one thing that you will see here is some of these pins here are longer than the others, and the same on the bottom. You can see these ones are all longer, these ones are longer, and those are the ground pins. I did the footprint for this edge connector specifically so the ground pins would all engage first. So this is something that I've had to change. I'll just chuck this in. Boink. That's how easy it is to load a module. Yeah, so let's go back to here because I want to show you what I changed on here. Now you can see if we zoom in on this edge connector, it no longer has these pins on the top being longer. So we've got longer pins on the bottom, which is the blue layer. We've got, which are the ground pins, and you can see the ground pins on the top layer are also longer. But I edited this footprint.
Henrik Ostrov said, at least I missed it, I think, but was there marking what way to insert them?
Ah, yes, Henrik. Okay, I will get to that in just a second because I'm just about finished with this. So what I did here is the pins that are the voltage reference pins. These used to be ground pins, but they are now the voltage reference pins for the I/O blocks. I changed the dimensions on those pins to make them shorter, so they no longer engage until ground has engaged. That way you can't get one of the VIO pins engaging before ground. So the footprint on this edge connector has also been changed. And I'm going to have to get rid of these vias on this particular thing because I need to route the VIO pin out up to the up to the appropriate place on that connector. Yeah. Okay. So Henrik asked if there was a way to set the orientation on these. Yes. Well, it doesn't physically stop you from plugging it in either rotated or offset. You could plug it in half misaligned if you wanted to, just like you could with an IC or whatever. But it has a pin 1 marking here on the silkscreen, and the module itself has, no, not that one. Oh, I think I might have closed it. Oh, here you go. In this model you can see. So the module on the silkscreen has a marking on pin 1, and there is a marking on pin 1 on the Testomatic board as well. So you just have to match up pin 1 there with pin 1 there. And looking at this, because it is largely covered by the socket, the highlighting on that pin is not that obvious. What I should do is bring it up a little bit so that it's visible above the socket perhaps. So for example, if I come into this mode, I'm going to grab that. What's my grid set to?
Scott Miller said, silk on the Testomatic board is hiding.
Yeah, so what I need to do is something like this. And then move the sides up as well so that we don't get that funky little notch just in there. I can fix that. So move that. Well, not moving, I'm copying So I'm duplicating that. And let's see if I move, oh, the problem is if I move this edge, yeah, it's going to move that as well. That may not be such a big problem. Oh, it's just kind of ugly. All right, I don't like half-assing things.
Said, can you just add beside there text 1?
Text 1, I could. That is true. I could just put the number 1 next to it. But what I'm going to do as well is I'm going to do a 0.508 millimeter line on the T-place. Let's just see how this one turns out. Oh, maybe what I should have done is come out wider here as well, like to there and there. I wonder how that, I'm going to try it on this and then push it to the 3D view and see how it turns out. There, 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 and there. Alright, save that.
Scott Miller said, double the thickness of the original box.
Yeah, the thing is that I need to do it by, I can't just double it from the center line. I have to go out because otherwise it'll overlap on this gap between the pads and it will overlap with the pad there. So I'm going to drop out of single mode, throw down the polygon. Oop, I want that. And then push to the 3D view because I want to see how this turns out. Where are we at? 11:32. I haven't actually done anything today. I've just been talking about stuff. Mostly talking about things I did. John John Whips asked, sorry, I have missed a whole lot of chat, as is the usual thing. John asked, do the voltage reference pins not have to be longer to enable voltage to be set before I/O pins make contact? Say halfway between length of ground pins and I/O pins. That is a very valid question, and it requires very valid thought. Yeah, I think this works. I think doing that, although I'd probably also want to put it wider down the right hand side, not just that way. Yeah, I kind of like that. So I'm going to go back to this. No, this. No. Where am I? Where's the board layout tab? So what am I doing? Oh yeah, I was thinking about what was I thinking about? I don't know. Oh yeah, thinking about the length of those reference pins. Yeah, do they need to make contact before the I don't know. Even doing a zero brain required task like this, I have trouble thinking about that. Yeah, this sort of job, doing these boring sorts of things, it's the sort of thing that I normally do when I'm like, this is where I will have a show on. I'll have something up playing and keeping me entertained while my hands just do the whoop. Let's put that one down first. Yeah, while I'm not thinking about this. But it is almost impossible for me to engage in conversation while I'm doing this. I don't know why that is. Maybe it's that I can consume information while I am doing a...
Henrik Ostrov said, I think it's better if they are longer just in case.
If they are longer... I missed the alignment of the center point. There we go. And snap there. And snap there and there. How close am I to done? Not very close. Alright, I'm going to subject you to this because otherwise I am going to forget about it. And I should do it before I forget. I'm going to end up with one of these headers without the silkscreen finished. Yeah, that's right. So I can... What can I do? I can do something like have a TV show on or a movie and be half paying attention to that and just zoning out while my hands are sitting here doing this, like putting silkscreen in place or routing tracks, solving the puzzle. But I find it very hard to talk while I'm doing this sort of thing. That'll do. Okay. However, I think we got there. I think that's going to be obvious enough, Henrik. Let's save it before I go too much further, just in case Fusion does one of its spectacular explosions. And 3D is out of sync. Yes, I know. Let's rectify that. And re-render, 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 and almost done. Almost done. Come on. Rendering done. Oh, did I throw? Yeah, I did throw the polygons down. The polygon pause were done.
Henrik Ostrov said, yes, that cool as well better than it was.
Yeah. I think that's going to be pretty obvious now. It should also be fairly obvious because the writing on the test module that plugs into this, I shouldn't say test module because that's the name of the thing that plugs into the PCI connector. The text on the I/O module will be oriented the correct way around. Now, there is an issue here which I have not resolved. And that is, if you need to replace one of these I/O modules, how do you do it? And doing it with the chassis in place is going to be really hard. I want to find that that 3D assembly that I had. Where did it go? Because what I might need to do is exposed... No, go away. Is
Scott Miller
exposed...
said, conmod.
Conmod? Conmod. Conmod. What does the con stand for? Testomatic 1, no. Oh, I'm in the archive here. TM Riser. Because I was looking for the 3D model before. How about in chassis? Is it in here? No, that one was updated 10th of the 2nd. I'm looking for one that was updated like recently, within the last day or so. I could, or maybe in test modules, TM no, module, test assembly, module plate assembly, no. I'm going to have to resort to just doing a search in a minute. It's not Testomatic assembly.
Henrik Ostrov said, let's make a machine that will change the modules, haha.
I don't want to search. Yeah, right. Use a robot. I'm going to have a lot of assemblies if I do a search for this. I want to do a search just within this project. Maybe I missed the option for that. Searchy, searchy, searchy. Okay, now can I... TM module assembly, Testomatic assembly, 16th of the 2nd. That's more recent, but it is not totally recent. Can I sort by TM module MGM, PCB assembly? So the PCB assembly is the one I'm going to open that anyway. Should already be open. Yeah, this is the one that I was showing you the screenshot of earlier. This is what I used to take the screenshot to stick into the into GitHub. Now you can see that it hasn't updated because this assembly is still referencing the old v2.2. So we'll update the components, and now the silk screen should get better on this. It'll get bigger and more obvious. There we go. So that's now showing the most recent version. Chassis assembly, 10th of the 2nd. UT61E Wi-Fi assembly. I don't know what has happened to this module. It's like, it's weird. Where has it gone? Yeah, and I wish I could sort by date, but even by date there aren't that many in here. 10th of the 2nd. There is one that I did a replacement on with the PCB. So, okay, this has been updated. Has it been saved? No, that hasn't. This one has been updated but not saved.
Scott Miller said, you hallucinated about making it.
Yeah, I must have. Alright, so what I'm going to do is change it on this one. Or maybe I just didn't save it. That is quite possible. What I might have done is modified this one, like updated the component, and not saved it. So let's hide some things so we can see what's going on. We'll hide that side plate, and we'll hide, where is it, that, and we'll hide that. Okay, now what I'm going to do is replace the component, which is this PCB. So this is the v2.0 Testomatic PCB. You can see the USB socket is quite high, the hub is high, it's got these connectors up here. So this component is this one here. I'm going to go replace component, and I'm going to pull it from Testomatic PCB assembly. That's the one I want, because this is the one that has modules in it. And we'll see if it goes into the correct place. No, it hasn't. Okay, so it is just put it into a random, well, not random, but not where we want it location. So I'm going to couple it onto the, look how weird it looks because we're in orthographic camera view instead of perspective view. It looks like, this is such an optical illusion. It looks like the back of the board is longer than the front of the board. It's actually not. On screen it is the exact same distance. If I put a ruler on my monitor, the distance from there to there is the same as the distance from there to down there. But it looks like it's, you know, getting bigger towards the back. Our brains are fooling us. It's actually exactly the same distance. But woo, look, it gets bigger towards the back. So I want to make a joint. No, don't get any ideas. All right, I'm going to match the edge of that hole to, oh, come on. What's going on there? Why is it, yeah, it is the origin of that. I don't know why it was doing that weird rendering thing. And I want to move it to, oh, come on, spin back around. I'm getting seasick. I want to move it to match up to the end of that mounting lug. Yunk. There we go. And did it take its modules with it? Yes, it did. Okay, so that is now bound in position on the mounting spacer, and all the modules are in position. So what we've got is these relays protrude a little bit into here. I've got a cutout in the deck now to allow for it to go around those relays. I could bring it slightly further in. That gap doesn't need to be that big. But anyway, on these G5LE relays, is my memory correct? What type are they? I can't remember. I think they're G5LEs. Omron something. Anyway, yeah, whatever those relays are, they come in a couple of different case styles. And when I did the original mechanical design for this, I designed it based on the style that is physically a lower profile. And then I bought some more, which were of the alternative profile, and they wouldn't fit anymore. So I had to physically hack the acrylic. I actually cut it with a saw to make that deck fit in around it. Is it on this one? On this chassis? Yes. In fact, the funny thing is, this is such a crude hack. I'm going to show you this because it's kind of funny. I was putting on these relays and I ran out. I'm going to turn this over in just a moment so that you can see it. 2 relays were the low style, and then I ordered some of the other type because I couldn't get the low profile type anymore. And the result is that there are 3 relays here, which are 2 different sizes.
Anytime you need to replace one, something has balked already, so having to open up the case should NT be that much extra work.
Yeah, that's a good point. All right, I'll get back to that in just a second. So you can see here that I physically cut this chassis plate to clear around the back of this relay because it's a higher one than the other 2. And then allowing for that, I added that rebate around it in the deck. So in the design, there is now a rebate across all 3 relay locations, and that is to allow for either style of G5LE relay. Is it a G5LE? I'm gonna GLE 14. Yeah, whatever. Anyway, I can't remember the specific part number of that variant. So yeah, there is that. Okay, so now what we have is down in this area. This is where there is now the row of I/O modules. The USB module, the USB socket that you can just see through here, it's not very clear through the acrylic because of all the reflections, is now moved further down. So, yeah, Scott said, anytime you need to replace one, something is balked already, so having to open up the case shouldn't be that much extra work. Yeah, but opening the case is a bit of a pain because there are so many steps involved in getting to this PCB. You have to take off a lot of the structure to be able to get the deck out, which is one of the limitations of my current design. You start by taking off one of the sides because the deck is interlocked into the side with these tabs. So step 1 is you take off at least one side, then you take off the back, which is a bit of a pain because it's got all of these things attached to it. And then you can slide the deck out horizontally, like you can slide it to the left to get these tabs to clear. But of course that requires you to clear, the edge of the relay. So maybe the other side should be the one that you open. Yeah, but what I'm thinking about, yeah, you can see these I/O modules now are pretty much in line with the deck. The deck is going to come down. This is one of the things that will work in my favor. At the moment, the height of the deck is dictated by this fan, which is sitting on top of the USB hub. So my plan is to move this fan onto the side wall. I'm going to put it over here. It's going to go right here on the left side of the enclosure. At the moment it's on the rear of the enclosure. I'm going to put it on the left so that it blows almost across the Raspberry Pi. But more importantly, what that allows me to do is move it down because it's sitting stacked on top of the USB hub. I need to be able to lower the deck. Now, if I can bring the deck down, it doesn't have to be all that much, but if I can bring the deck down, these I/O modules will be exposed in this cavity, and I think that it's going to be possible to replace them without removing the deck. There should be enough clearance to get in here to do it. It'll be kind of awkward, but you could do it. Might need like a little hook or something to get under the bottom of the module. But imagine if this deck was lower. In fact, imagine if it was kind of significantly lower, like 10 millimeters
Amanda
lower.
Thompson said, design a cross support so the deck sits on the supporting cross supports that you add.
Wagon Load says, why can't you make the screen open like a car hood and make that area where you plug in the I/O mods? That's an interesting idea. That would require a total mechanical redesign, but it is an interesting idea.
Scott Miller said, redesign the desk to slide out the back.
Yeah, so Scott said redesign the deck to slide out the back. That is an option. And also Paul asked the very valid question, which is, do you need the deck? If it is too annoying, I'll remove it and leave it out if I ever need to replace the modules. Yeah, technically you don't need it. It's just to provide some more structural support to the chassis itself, because it ties the two sides together. Instead of having verticals like a box with no top, it turns it into a box with a top, and it makes it much more rigid, but it's probably not required. And then, yeah, and also it just protects all of the stuff in under here, like the Raspberry Pi, keeps it all neat, because there are cables and other things in there. But yes, you're right, the deck could be optional. And also Amanda said something about it. Where was it? Yeah, Amanda said design a cross support so the deck sits on the supporting cross supports that you add. That's another valid approach. Instead of having it interlocked into the sides, as I currently have, there could be like a cross brace somewhere along here, just a cross piece and then another cross piece towards the back, and the deck could just drop into place and sit there. All valid ideas. So I think what I'm going to do is and Paul says shorten the deck towards the back. By that, do you mean just remove this front part of the deck and have it more open at this front section? That's possible. Yes, so what am I going to do? Relocate the fan and the fan control module. That's actually what goes on here. So there is a fan control module that bolts into these two holes, which is has a temperature sensor, so that if the inside of the chassis here becomes warm, it turns the fan on. Now, I've never actually seen the fan turn on, and the thing is that this fan may be irrelevant. It might turn out that it's not required at all and it can just be deleted. But I didn't like the idea of a Pi 4 sitting inside an enclosed box and doing stuff and potentially getting warm. So by allowing for a fan, at least it means that we can force some air across it and keep it cool if necessary. So for now, I'm going to keep the fan, but it may just never turn on, in which case it's not required. So I think my plan is I'm going to relocate the fan to the side, put it right about here, and lower it so the bottom of the fan is just down near the deck to give me the maximum possible scope for lowering the deck. Then the Crispian says, you mean it isn't a pie warmer? And John said just sufficiently rebate to remove the modules. Yeah. Oh, and Tech Nebula says, I can remember when the Testomatic was discussed, the deck was mentioned as to protect the part below and avoid pointy finger, as well as avoid parts falling in. Yep. I want to keep the deck because it makes the whole thing much neater and safer, but I want to lower it. And that will then expose these. And I think that solves the whole problem. Now, how much can I bring it down? Oh, that's the chassis assembly. Okay, I'm going to go back out of there and into chassis. Where is the back plate? Okay, let's have a look at the back plate design. So this is where the fan currently is, and what have we got here? Edit sketch. Alright, so this is the sketch that defines the back plate, and it's got the fan here. What is that dimension? What is it? Dimension 47? No, that's the from there to there. That's 20. Oh, stuff it. I'm just going to do an inspect. 50 millimeters. Okay, so the fan is 50 millimeters square, and the control module, which is this spot here, is also, it's 47 millimeters. Okay, 50 by 50. Rotate the power connector 90 degrees. Yeah, that's no problem. I can rotate that 90 degrees, which then allows me to bring the power switch further down.
Scott Miller said, rotate the power connector 90 degrees.
Yep. Oh, and look, the USB hub is 11 millimeters thick. So, and what is our current height? So if we have a look at the distance from there to there, it's 63 millimeters. So if we drop that by 11, we could make that 60, we could make it 50. If the, if we made it so that the fan just fitted in, like it sat on the base and the deck sat on the fan, pretty much, we could drop this by 13 millimeters, because we've got 63 millimeters at the moment as the gap between the top of the base and the bottom of the deck. And we could make that 50 millimeters. Yeah, I reckon that would work out nicely. So then that'll drop us 13. Let's have a look in the chassis assembly, because I want to see what the distance is. The distance, can I do a dimension from the bottom edge there? Is this going to give me a horizontal distance, or, oh, it's going to give me a, yeah, it's going to give me a hypotenuse distance, which is not what I want. I want a vertical distance. Can I do a measure? Let's cheat. I'm going to do a measure from the bottom edge of the module here, and I'm going to measure it to, I don't know, let's just measure it to this pin, that face of that pin. There. Okay, that is 8.75 millimeters. Ah, cool. Okay. I can see this coming together. So if we can drop this deck by 13 millimeters, that means that we are going to have the top of the deck 4 millimeters below. Oh, I'm going to run into problems with these connectors now. I solve one problem and make another one. Yeah, so I would no longer need the cutout for the relays, because the deck would go below the relays just, and the top of the deck would come in about here somewhere. Well, doing this mechanical stuff now is good, because it means that I can see all of these issues before I send the PCBs off for fabrication, and then I've got time to fix it, potentially. I might be able to move, no, I can't be bothered. I was just thinking I could move all of these modules up as well, because that could be, I could fix the routing on that. There's a bit of space up here. But no, I'm going to leave those where they are. And I will do something about the infrared camera connector and the external button connector. But first, I'm going to redesign the enclosure a little. I'm going to drop the deck by at
Henrik
least...
Ostrov said, new cutouts for the connectors just.
Yeah, just like a little notch out of there for the connectors. One of the issues is that these, I don't even have a plan for where these are going to go. The infrared camera, we need to get back to at some point. That can be one of the Project Dopamine projects But in fact, I think it is on the spreadsheet. The IR camera is going to need to go to some external connector so that it can then go up the chassis onto the top gantry, because the infrared camera is going to be mounted up here somewhere and pointing down at the device under test. So possibly on the back, because there's going to be a mechanism on the front for the clamping mechanism to push the pressure plate down onto the device under test. And all of this is speculative because I don't even know if the infrared camera is going to work through the pressure plate. We may not get any sensible temperature values out of it at all. This is all a bit of an experiment. Yes. Okay. So I'm going to move that to there, drop the deck, check the clearance on these modules, check the clearance on these connectors, and report back to you, I guess. Yeah, making all of those changes is just kind of a tedious thing. It's something that just takes time, and I'm not going to be able to talk while I do it. So doing actual tricky engineering work or brain work while I'm doing a live stream is very, very hard, for me at least. So maybe people would be interested in having a live stream while I'm working on it, and make it so that it's not like one of these Sunday live streams where I'm giving commentary continuously. I basically talk for 2 hours straight, but one where I'm just working on it and you happen to be looking over my shoulder, and I may or may not say a single word. I could just be working on it while you watch. I don't know if anybody would be interested in that, but that's a possibility. What is that doing there? Oh, these things are in the wrong place. Why are they there? That is very weird. Because I made them invisible down here, side plate. And, oh, there are others there. That's weird. What part is that? It is cap plate. Oh, there are some other parts that I've designed, but that's not meant to be there. That's an old cap plate. Why is it there? Cap plate. That's the top cap plate. What about this one? That is... yeah, weird. I don't know. There are some miscellaneous parts hanging around in the model here that are duplicates of other parts. That's strange. Because those parts still exist. One of them was that little spacer plate in there, and that spacer plate in there. I don't know. It's a mystery.
Mitch Davis said, at Mitch Davis.
Where was Mitch's comment? Oh, John's ASMR live stream. Oh, and someone asked, but could you hear us screaming at you? Probably not. Wagon Loads asked, why is the pie there and not under the screen? Yeah, this has been brought up a couple of times on Discord. And switch to perspective view. Yes, camera perspective. At least now it looks more natural. Yeah, it's been brought up a few times in Discord. Like, I think it's been asked twice in the last week why the pie is here and not under the screen. Or there was a suggestion about using a different screen, which has...
squirrel-free stream. WTF.
Yeah, I know, Scott. What's going on? It must have been the 2 coffees I had before starting. It acted as medication for me. Keep the ADHD at bay. Yeah, so and there was a suggestion of using a screen that has the Raspberry Pi attached directly to the back of it, which I have actually used in the past, and I've got a few of those screens. In fact, I think that's what's on the first, like the current Testomatic version 1, the one that is in active use right now, the one before this, has the Pi stuck on the back. The problem is that I need access to the I/O header, and so the Pi really needs to be exposed. And more than just the I/O header, I need access to USB, to Ethernet. I need access to, let's see if we can zoom right in here. Whoop. I need access to the 40-pin I/O header. I need access to HDMI. Well, no, I wouldn't need HDMI if it was on the back of the monitor. And having it exposed here is just a whole lot easier than having it stuck on the back. It's a compromise. Either you put the Pi with the screen and then your screen cabling is neat, but everything else is a pain in the ass, or you put the Pi separately and then all of your other cabling is easy and connecting to the screen is a pain in the ass. But in fact, it's actually not that much of a pain because it's just a low profile HDMI cable that goes from the side of the screen, comes through and plugs into the Pi. So it's actually significantly easier to have the Pi separate and mounted here and linked by a low profile HDMI cable than it is to have the Pi in the front here and then have to figure out routing for all of the other connections that need to get to it. So this is definitely the better location for it than trying to put it on the back of the screen. All right. As they say, and our amp power is up.
Mitchell R said, just saying, if you did CM4, CM5 board, the back of the main back is CM4 fifths, then it resolves all these issues, lol.
Oh, okay. Yeah, CM, I could do a CM, but then I'd have to do all the breakout myself. There are lots of compromises in this design, but I think this is an adequate compromise. I would rather buy an off-the-shelf Pi and have a 40-pin dip like a 40-pin IDC header that just plugs into it, rather than try to make a carrier that integrates the CM4, and then I've got to add USB and Ethernet and all of those things that I get just on the board with an off-the-shelf Pi. In this situation, I don't really see the benefit of going for a CM. I think a standalone Pi is the correct solution in this situation. Stephen says CM5 has 2 USB 3 ports and a USB 2 port. USB 3. Interesting. Yeah, David said. TTS will catch up, maybe. I will say it for him. Are we even going to finish almost on time as well? Yes, we are. Because I am going to wrap it up. What am I going to do? I am going to get something to eat, and then I am going to make some changes to the chassis, because I want to make those changes before I send the board off for fabrication. I need to know that the changes I've made to the PCB with the location of those test modules is suitable for the chassis. It all must work in harmony. So I'm going to move this to the side. I'm going to probably make this horizontal so that I can then lower the power switch, lower the deck by somewhere between 10 and 13 millimeters, to be determined, and check the clearance on here and how the deck then interacts with the modules and the relays and these sockets. So I might have to do something about moving those sockets. Yeah, but
Henrik Ostrov said, I'm so full of that chicken, it was so good, ma ha ha ha.
ah, Henrik, you're like Pete. Pete always used to be going on about pizza right about now and making me hungry. He hasn't done that for a while.
Scott Miller said, and swap the fan for a Noctua NFA4X20.
An NFA4X20. Let me see what a Noctua NFA4X20. Is that like a 20 millimeter fan? Optimized Ford. in size 40 by 20 millimeters. What? That's a weird... Oh, is it 40 by 40 by 20?
Mitchell R said,
Okay.
next step, Poe-powered test board, so only a single cable more, haha.
Yeah. Could run... I could run PoE off it, maybe. Yeah, okay. It's a 40 millimeter fan instead of a 50 millimeter fan. That would be nice. Yeah, well, if I design it for the 50, then there's plenty of room for the 40, so that's fine. All right, so I am going to leave now and get some food, but in the meantime, okay, so Gerald asked, what's the next thing on the to-do list? Yeah, the whole unit PoE. Yeah, I got what you meant, Mitchell. So power over Ethernet, plug it into the back of the Testomatic, and the whole thing powers up. The Raspberry Pi, the screen, the whole thing. Yes. And next Sunday, don't forget, Belgrave Survival Day. And yeah, I will report back. Thank you everybody for coming along. And where's the button? There it is. Okay. And I will talk to you really soon. Thanks. Bye.